All right, next we're going to talk about scatter plots. We're going to talk about how we can put data on the coordinate plane, as well as how we can put a line to fit that data best. We're also going to talk about scatter plots that maybe they don't fit just one straight line. Those are called nonlinear scatter plots. And then we'll take a look at Desmos and see how to actually graph a line of best fit. So a scatter plot shows us these data points, and I'm sure many of you are familiar with these different types of graphs. We have information on the x-axis and information on the y-axis. Uh, so we can have multiple y values that are associated with one x value. For instance, if we look here at number 4, there are two different y values for number 4. And that's allowed because these are just data points. And specifically, if we look at the x-axis, this is number of teeth lost, and the y-axis is the age in years of the person. And we can start to look at trends of this. So as the number of teeth lost increases, the age in years is also increasing with this. This is what's referred to as a positive correlation. As one of the variables increases, the other variable increases as well. And we can start to make predictions, sort of like how we made predictions with our ratio problems with this smaller subset of data, and then compare it to an entire population. So this is the same scatter plot, and this slide just says that there's a positive correlation between the number of teeth lost and age. And so that means that as one goes up, the other goes up as well. So we should have a trend where we can have what's called a trend line or a line of best fit that goes along with these points. And I just roughly sketched one. Um, there is a way to actually figure out exactly what that equation of that line is. Um, and that's called the line of best fit. This is the line of best fit for this particular data set here. Now, if we go to Desmos and we type all of this into Desmos, we can find what the line of best fit is. I'm going to share a different screen. I'll share Desmos screen here next. So all I'm doing is I'm copying the X and the Y values from this scatter plot. So we're going to start by pressing the plus button, select table, and then we can type in the X and the Y values. So the first point that's on our scatter plot is 3, 2. And we can see our points there. You can change the color of these two. If you want to, you can change the colors. That's perfectly okay. The next ones, there's 4, 2 is one of our points. 4, 4. So all of these table values are associated with these points on the graph. 5, 5 is another one. 5, 7. 5, 8. 6, 4. 6, 6. 6, 12. 8, 12. And the last one is 9, 13. All right, so this is the same data from our scatter plot. Now that we have all of this data, we're going to go down to line number 2, and we're going to write this specific equation. Now, you might have a question like this on the SAT. You might not. But if you continue math courses, this is something that's I think is useful to know. So you're going to type y and then shift minus. So that makes a subscript and then a number 1. You go over and then you type shift, and it's the number to the left of the number 1, and that's I just call it a squiggly sign. It means about equal to. And now we're going to say that's about equal to mx subscript 1 plus b. And again, you do the subscript, you press shift minus. And that's telling the graphing calculator to graph a line of best fit based on this table data for the X1 table data. That's what the X1 represents here, and the Y1 table data represented here. And now we can go down and we can look at what this equation actually is. So all of our equations are in the form y equals mx plus b. All of our slope-intercept form equations are. And it tells us what m is. It says it's 1.92308. I'm going to just estimate and just write a number very close to it. 1.923. And for the b value, the y-intercept is at negative 3.846. And as you can see, the red line is the same thing as the blue line. So that's how you can find what the line of best fit equation is, if you're ever asked to do that. All right, let's go back to the slides here. Okay, this next question is asking us about interpreting what the data set is telling us. So it says Sarah plotted the sales of hot drinks at the Crazy Teapot Cafe against the outdoor temperature in degrees. Which of the following statements about the data is correct? So here we have to look at, first of all, what the X and the Y axis is. Is the X axis increasing as we go left to right? It normally does. It is. And the sales of hot drinks, the Y axis is increasing as we go up. It normally does. So now let's take a look at what's happening here. So as the temperature goes up, what's happening with the sales of hot drinks is as X increases, Y is decreasing. And really, I should have said it like Y as Y goes down, because we write our slope like change in Y over change in X. So as Y decreases, X increases. So because one is going down and the other one is going up, maybe I should say increases like this, but X does go left to right typically. But anyway, so as Y goes down, X is going up. And so this is a negative correlation. Now we have to see what that actually means in terms of our choices from the multiple choice. It says hot drink sales decreased as the outdoor temperature decreased. So here the temperature is increasing and sales are decreasing. So A is not correct. It says they both are decreasing. Now it's important not to mix these up. I know that we have one going down and one going up. So it's important not to mix these up. Hot drink sales increased as the outdoor temperature decreased. So the drink sales, it says they're increasing as temperature decreases. If we take a look at our graph, as we read it from left to right, temperature is increasing and drink sales are decreasing. Now this B looks like it's the opposite of that, but what's kind of interesting is we can read this the other direction if we read it in the backwards direction on the x-axis and on the y-axis. So the hot drink sales increased. So let's see what's happening. These are going up, and it says as temperature decreased. So if we start going from this way, if we start at this point here, we can see that the drink sales are increasing as we go up and up and up. And we can also see that as we go up and up and up, the temperature is going down. So in this case, it is B. So that's how you can interpret the graph. Sometimes you don't read it left to right. Sometimes you can read it right to left. And we talked about the line of best fit and looking at actual data. This is another example. I think maybe there's just a slight typo here on the y-axis. This is supposed to say resting heart rate beats per minute. And this is hours of exercise per week. So let's take a look at what's happening here. As hours of exercise is increasing, the resting heart rate is decreasing. So as we exercise more by 1 hour, it looks like the beats per minute are going down by kind of maybe close to about five, um, maybe a little bit less because it's not exactly five each time, but it is going down by the same amount each time. So our resting heart rate, it's just what your heart rate is when you're just sitting completely still. As your heart gets stronger, your resting heart rate should go down because it's getting stronger. And that's what's happening on this trend here. So these scatter plot points are from they're from different people that were probably sampled from this data. And because this data exists, we can use the line of best fit to make predictions about other people in the population. So notice that not all the dots are exactly on the line, but they're very close to what the line is. Now we have an actual function for this line of best fit. So it looks like if you were to plug in all of these dots into Desmos like we did earlier in the example, and then do the line of best fit equation, you would get this for the equation. And R of H basically just means Y, and H just means X. So a lot of times we'll see functions like F of X, G of X, H of X. R of H is just another way to write one of these. So R of H is basically just Y, and H is basically just X. So all of our equations are in the form Y equals mx plus b. Or I shouldn't say all of them, but most of the time they're in that form. And m stands for the slope. And so here our slope is negative 4.17. And our y-intercept is 80. So our slope is m, negative 4.17. And our slope is rise over run, which is the same thing as the change in y over the change in x. But here we just have a decimal. So you can always write slope as over 1 to get a better idea of how to write the run when it's not given to you. So now what this means is it's going down 4.17 spaces, and it's going over to the right 1 space. And this should probably be some review for how to graph the slope. So down 4.17 over 1, down 4.17 over 1, and the pattern is continuing. So it says, what's the meaning of negative 4.17? Well, that means if we go down 4.17, that means our resting heart rate is going down by 4.17 beats per minute for every 1 hour of exercise. So that's what part A is. Part B says, what is the meaning of the 80 in the equation of the line of best fit? If we look at the 80, that corresponds with 0 hours of exercise. And so that would mean that after no hours of exercise, the resting heart rate of a person would be 80 beats per minute. All right. Now part two of this, it gets a little bit more interesting. It's asking us to apply this in a more logical sense with a real world application. So this graph shows the resting heart rates from the people still. It's the same numbers and it's the same equation. But C, it says, according to the line of best fit, what is the expected resting heart rate for someone who exercises for 10 hours per week? So for 10 hours per week, that's when H equals 10 or when X equals 10. And we know R of H, that's the function. So we would just write R of 10 equals negative 4.17, plug in 10 for H, and then plus 80. That's going to be 41.7 plus 80. And we're going to get a decimal answer of 38.3. And so that's the theoretical resting heart rate for somebody who exercises 10 hours a week. Now, that's a very, very, very low heart rate. Some people might even argue that that's dangerously low, um, for your heart to be beating that slowly. But that's what the line of best fit is telling us. Now let's take this a step further and see what R of 20 is. So R of 20 would be if somebody exercises for 20 hours per week. So maybe some of you are track runners or where you play other sports like football or volleyball or basketball. And I'm certain you probably get close to exercising that many hours per week if you're an athlete. This says if R of 20, so 20 hours of exercise equals negative 3.4. So it already did the math for us. And it says, what does that mean? Well, this means that the line of best fit trend is telling us that if we continue to make estimates based on this line of best fit, that when we plug in 20 for the function, we get negative 3.4. Negative 3.4 means that someone's heart would be beating negative 3.4 beats per minute. And that's impossible. If someone's not alive, their heart rate is zero. So a negative makes absolutely no sense at all. All right, so that's how you solve these problems for generalizing with larger populations. Sometimes we have scatter plots that are nonlinear or quadratic or exponential. Just make sure that you are determining that properly. So this could be, I mean, if the line wasn't there, you might maybe think that it's linear, like you could approximate, and you could do a linear approximation of it. But here it tells us that there's a line and it's showing it's a curve and it's giving us a lot of quadratic options here. And this option for the linear option doesn't really make any sense. So we can cross out A right away. We can also cross out D right away. And the reason we can cross out D is this number is a positive. That's our leading coefficient and it's positive. If our leading coefficient is positive, our parabolas are going to open upward. If our leading coefficient is negative, our parabolas are going to open downward. And so that's what's happening here. It's opening downward. Now we've got to figure out which one of these equations is this? Is this B or C? Well, first of all quadratic equations are in the form ax squared plus bx plus c. So that is definitely something to memorize. And this tells us as well here, we can eliminate A and D. We have to determine between B and C. So I like to solve it this way. It says since it's less than 5, it must be B. I would rather we talk about this solution instead. So if you know it has to be quadratic and you're choosing between B and C, let me copy these really quickly to the next slide so we can examine these as we look at the answer options. Okay, so it says B or C. So the first thing that I would do for this problem is to examine where's the vertex located. The vertex is the highest or the lowest point, depending on if it's opening up or down. Here it's opening down, so the highest point is the vertex. And the vertex is somewhere maybe around about there. And sometimes your teachers, you might see them draw the vertex like this. The equation for the vertex, so all of our quadratic equations are in the form y equals ax squared plus bx plus c. And the equation for the vertex is, for the x coordinate of the vertex, it's x equals minus b over 2a. And so let's check answer B first. I'm going to write uppercase B so we don't get confused. So uppercase B for minus B, B and B for uppercase B is positive 3.5. So if we do negative 3.5, that's why we get a negative there. And then 2 times, and then A is negative 0.2. And that equals a positive value, 8.75. And you can see that they did the same thing for C down there. I just wanted to write the steps there for you for B. But we do the same thing for C. Now, this means the x coordinate is 8.75 for the vertex. The other option is negative 8.75 for the vertex. And here, we're on the positives. So it can't be C because that means the vertex would be like somewhere way over here on a completely different side of the graph. So that's how we can select by process of elimination. All right, this next one says, which of the following equations most accurately fits the data shown? And honestly, I should probably be showing you how to do this on Desmos because this is, you get a graphing calculator on Desmos. So of these different choices, you can plug in all this information into Desmos. That might save you the most time. But another way is to look at, is there exponential growth or is there exponential decay? So I was going to show you Desmos, but let's actually go back here because there's a much faster way to do this. So if this is one of your last questions and you have extra time, you can type it all in, or if you're good at typing, you can type everything in quickly. But this says, which of the following most accurately fits the data shown in the scatter plot? So this is a growth, exponential growth, because it's going up. It's exponential because it's not a straight line. And it's not quadratic because it's not starting to go in a U shape, but it is starting to go up faster and faster and faster and faster as we increase on the x-axis. So something to know about exponentials is they're in the form y equals ab to the x. If b is greater than 1, then it's going up. If b is less than 1, then it's going down. So it's got to be answer choice C. Now, if you're stuck between C and D, let's take a look between when we have a positive exponent and a negative exponent. So it can't be A because that's linear. Can't be B because that means that it's going down. It's less than 1. So we would actually have a graph that would start to look like that. But let's look between C and D next. I'm just going to get rid of all this. So for C is 7.5 times 1.1 to the power of x. And for D, very close, 75 times 1.1 to the power of negative x. And I'm just using my keyboard. You can type all this in by going down to the keyboard here. You can do exponents by clicking, let's see, want to do 1.1 to the power of something. That's how you do squared. If you need it to go to the power of x, you just press this button here and it brings you up to the power. And then you can type in a letter or you can type them in there that way. All right, so C is the green and D is the purple. So the green's going up, so it's increasing. The purple is going down and it's decreasing. So because we have a negative exponent, our graph's going down there. All right, so that's everything for scatter plots. Again, just make sure to use the line of best fits, and also remember that sometimes that's not always the best the best way to represent data if we're generalizing for larger data sets.